Before we go on to second order differential equations, let's just have a very brief reminder of first order differential equations that came up towards the end of course 1M1. Now, a first order differential equation is an equation linking a variable x, a function y, and a derivative dy by dx. So we have an example here, or another example here, where we have variable t, function z, and the derivative dz by dt. It's a first order differential equation because in each case the only derivative present is the first derivative. So those are first order differential equations. And when we talk about solving a differential equation such as these, the whole point is to write it in such a way that we don't have any derivatives there. Now, ideally, we'd like to be able to say that our function is equal to, for example, y equals, and then name y in terms of x, or whatever notation it is we're using. Sometimes we would have to settle for an implicit solution there. But when we first solve a differential equation, we will get the general solution, where we will have a constant. It's come from a constant of integration, and the solution containing the constant is known as the general solution. So, if we have a look at this equation here, dy by dx is 3y squared over 1 plus x squared. We can solve this one. We can separate the variables. We can integrate. Obviously, the details are in 1M1, and then we can rearrange, and we get that y is equal to 1 over a constant minus 3 times the inverse tan of x. This is the general solution, and it contains this constant c. Alternatively, we've seen the equation here, dz by dt plus 2z is equal to e to the t. This is one that we solve using an integrating factor, and we end up saying that z is equal to 1/3 of the exponential of t plus a constant times e to the minus 2t. Again, this is one which contains a constant. This is the general solution. But if in addition to the equation, if we're given one additional piece of information, we can find the value of the constant, and that gives us the particular solution. So, for example, going back to the equation here, if we were also told that when x is equal to 1, y is equal to 2 over 3 pi, we actually end up with a value for c, and we can write our solution y without any constants there. This is the particular solution. It satisfies the differential equation. It satisfies the condition that we have here. So this is a particular solution. Similarly, if we're told we have the equation here, and also when t is 0, we have that z is equal to 0. We can apply this condition, find the value of c, put it into the general solution, and it gives us the particular solution. So let's go on now, and we'll look at second order differential equations. Many of the principles, including, for example, the general solution and the particular solution, also apply for second order differential equations.